All right, let's get started. We discussed last time for models of hyperbolic spaces. And as I remember, so like in the end of the last lecture, I discussed reflections in hyperplanes and some consequences. Now let's focus a little bit more on that. So just, we'll start about, so a few more facts about reflections in hyperplanes. So recall that, so what we actually proved last time, we already know the hyperbolic, so the hyperbolic distances in our four models, right? We know the totally geodesic subspace as well as at least in the hyperboloid ball model, in the hyperboloid model. And I already defined reflections. So in the hyperboloid model, we have a reflection RH, right? So this is a hyperboloid model HD. We have a reflection RH that maps a point X to X minus 2 X E over the scalar product E times E multiplied by E, where H is just this orthogonal complement to the vector E, where E times E has positive Lorentzian norm, right? So geometrically, right now it's not that important. So geometrically, it looks like that. Here is some vector E, and our hyperplane intersects the hyperboloid. And so what do we know is that H is isometric to, well, yeah, it's isometric as a Riemannian manifold to HD minus 1, actually, and this is an isometry, right? So in the hyperboloid model, this is my reflection. So we know that RH belongs to the isometry group. Well, first of all, it belongs to, so my goal is to indeed show that O prime D1 coincides with the full isometry group of the hyperbolic space HD. So it definitely belongs to O prime D1. And this is isomorphic to the full isometry group of HD. And I actually want to show this, right? So the question is, why? These are isomorphic, right? Recall that OD prime, okay, so recall that OD1 is the set of matrices such that A transpose ID1 A is ID1, right? Where ID1 is my diagonal form of signature D1, right? Yeah. And yeah, definitely this belongs to GLD plus 1R. So these are invertible operators that, well, invertible matrices that preserve okay, invertible transformations that preserve this quadratic form. And OD1 prime, right, is the subgroup. And OD1 prime is a subgroup of OD1 such that O prime D1 of HD is HD. So I do not want to send it to the, yeah, I do not want to interchange the connected components. And obviously, RH indeed belongs to OD. Okay. Then, since we know that any point, since any point X in HD can be mapped to the point A, which is just with coordinates 1 and the remaining are 0. Right, since any point X can be mapped to A. But how? By an appropriate reflection, right? By an appropriate reflection, we reduce this question to the stabilizer of the point A, right? But for them, we already know that it should be an orthogonal group, and those are generated by reflections in hyperplanes. So since any point X can be mapped to A, by an appropriate reflection, we reduce well, so eventually I'm trying to, okay, it's not like a, so I'm trying to prove simultaneously two facts. That one fact is that the isometry group is generated by reflections in hyperplanes, and the second fact that these two coincide, right? But since I map any point to A, I already have that. Okay, so let me denote it as G, right? We reduce, I would say, this discussion to the stabilizer GA, which is known to be isomorphic to an orthogonal group, right? The latter is generated by reflections and thus so the latter is generated by reflections and thus the entire G is generated, right? But this already implies since On of R is naturally sitting in On1 prime, right? So this is, I should actually say that since GA, right? So the stabilizer of A in G is the same as the stabilizer of O1. Sorry, it should be D actually, yeah. It's a typo. So the stabilizer of OD1 prime of the point A is also OD. so to the stabilizer, and for this we know that this is American. So okay, this implies and here I will write since G stabilizer of the point A is also the stabilizer of this point in the group, not G, but OD1 prime, right? And and this OD. This implies that G is isomorphic to O prime G1, right? So that is, we have this important consequence of the behavior of reflections in the hyperbolic space. So we have to, okay, thus, I will just write it down carefully here. Thus, we just proved the following theorem, right? Theorem. Isom HD is isomorphic to O prime G1 and is generated and any isometry G from isom HD okay, is decomposed, can be decomposed into the product, right? Can be decomposed into the product of at most D+1 reflections. Okay, so these are our hyperbolic reflections. So what is nice, yeah, again, D+1, since I use one reflection, right, to send X to A, and then, well, basically to interchange A and X, the remaining D come from the orthogonal group. So obviously it can be much less than D+1 reflections. For instance, if it is a hyperbolic reflection itself, you have just one. If it is like a nice rotation around the codimension 2 plane, you need just two reflections with respect to hyperplanes intersecting along this codimension 2 plane, right? So that's the idea. But this fact is very important. And now I want to, okay, now I want actually to view this fact in the other, in some of the other models. Okay, but before doing that, I would like to say a few words about the boundary. So before moving to other models, recall that we already discussed the ideal hyperbolic boundary. Now I'm going to discuss it in a general setting. So recall that the ideal, sometimes it's said to be ideal hyperbolic boundary which will be denoted as D, maybe with this index, with the infinity index HD. Okay. The most convenient way is to start from the Klein model, right? But I can start with the hyperbolic model again. Is the set of set of equivalence classes of isotropic rays. It is the set of equivalence classes of isotropic rays. So I'm taking the vectors x from R d1 such that x times x is equal to 0. X0 is greater than 0 is positive, right? And I should take the quotient by positive. Okay, I will just write the group of positive real numbers, right? So I'm generically, it looks like that. I have this cone picture, right? I have the hyperboloid HD, but I'm taking only these vectors. Obviously, x is equivalent to any lambda x. So if I have, but I want to take the vector x looking in the same, right, in the same direction. So with respect to this coordinate, this is a positive direction, right? I do not want to take those guys. And they are equivalent, these two vectors, isotropic. Obviously, this vector is also isotropic, right? It's just, it belongs to the same line. So it kind of corresponds to the same point on the boundary where lambda is positive. So if lambda is negative, my vector will look in the opposite direction, right? Okay, so the set of, and now we can see, right, one can see that one can notice that D, so the boundary of HD projects just to the D minus one dimensional sphere. Okay, which is, yeah, which is the boundary of the Klein model. So it projects to under the projection from okay, P, or sometimes I will denote it as pi, but yeah, actually I'm not really happy about the notations I used last time. Probably it's a bit better to use it as pi, since usually P and Q are points in the space. Okay, but it's so under the projection pi from HD to KD, right? And remember that, so in this picture over here, yeah, we just project them to the boundary, right? So these are my, this blue is my boundary, which is obviously the boundary of the unit ball. In this affine chart, x0 is equal to 1. Yes, and this is a D minus one dimensional sphere. Yeah, I hope that this picture is clear. So topologically, it's a sphere. Okay. And an important fact, so it's like a proposition. any isometry, any isometry. Yeah, by the way, and we set HD bar as the union of HD with ideal boundary, right? And this is the compactification of the hyperbolic space. Any compactification of the hyperbolic space. And a remark is that it is topologically just a closed ball, right? It's homeomorphic to a closed ball in RD, basically. Yeah, closed ball. Okay, and any isometry F from the hyperbolic space HD, doesn't matter in which ball you work, right? So I will use here the notation which like covers all our models. So this is the hyperbolic space. It extends to a self-homomorphism. Extends to a self-homeomorphism, which I can denote as F bar from HD bar to HD bar. So one can, well, and this extension is like well-defined and unique, yeah? So you can view, and in fact, I would say that probably the best way to see it is to look on this in one of the ball models, since any isometry is generated by at most, well, okay, it's generated is not probably very well. It is decomposed into the product of some number of reflections, and we see that these reflections, they intersect the boundary sphere also in some sphere, right? So in fact, we can, the best way probably is to move to the to the conformal ball model. And that's what I'm going to do right now. So, okay, so the plan is to consider planes and hyperplanes in the conformal ball model. And along the way, we will see how to show this proposition. Yeah, how to justify this proposition. Okay, now I need to switch to the right board. Okay, great. This is okay. So again, reflections. Back to reflections, and planes in conformal models, right? In conformal models. Okay, now I want to say what actually is the reflection, what is the conformal, what the conformality means. So I think that yeah, I will just say that we have two types. We have conformal and anti-conformal maps, right? So we say that a diffeomorphism between two, so a diffeomorphism Let me denote it as, I don't know, phi between two remaining manifolds. Is a conformal, okay, is said to be conformal if the differential at any point is the product of the okay, let me say it. So if for every point P belonging to M, the differential df at the point P, okay, sorry, at the point P is the product of some dilation or Euclidean similarity or homothety. So I will also write a homothety. And an irritation preserving isometry. Okay, an irritation preserving Euclidean isometry. Okay, is an irritation preserving isometry. And I will include here that it is anticonformal if respectively here we also have the composition of dilation and some orientation reversing, respectively reversing isometry. Okay. So in particular, this is quite close to so this is just very close to definitions in complex analysis, like complex variables. And I will give an example. So an example. So the first and the second. The first one is just any Möbius transform is a conformal map, right? Any Möbius, or sometimes it's called fractional linear transform is conformal. This includes the example that is -1 over z, right? So in particular, -1 over z, which is a composition of an inversion with respect to a sphere and complex conjugation, right? Well, no, not a complex conjugation, which is a composition of a inversion and reflection. But for instance, any reflection is anticonformal. And I will write something like that. But minus, okay, but the map f of z, which is minus z bar, or okay, or h of z, which is -1 over z bar. Okay, does it preserve? Is anti-conformal, right? Are anti-conformals. Are anti-conformal. Isometries of U2, right? Isometries of H2 in the upper half plane model. Okay, let me check. Is this correct? I wanted to find this inversion with respect to so my picture is here. So one reflection is just with respect to the vertical half line, right? And also I want the inversion with respect to the unit. So if this is z, then this is going to be z over what? Z over the norm squared. Oh, probably it's just 1 over, right? Yeah, it's just 1 over. It's just 1 over the bar. So no minus here, correct? It should be the inversion with respect to the unit circle is just z over the norm. Since the product, no, wait, the product should be is equal to 1, right? The product should be equal to 1. Sorry, say it again. It is z here inside the circle. So it should be z with some multiple. It should be lambda z, right? Such that the product, right, the product lambda z, the norm, that is the norm lambda and z absolute value squared is equal to 1. Yeah, so I think it's, yeah, it's good. Yeah. And this is equal to 1 over the bar, obviously. So yeah, this is my standard. Yeah, this is my standard complex inversion with respect to unit circle. Okay, in the mole model is like a half circle, right? So it's a semicircle. And so these two are anti-conformal maps, and these are conformal maps. So for instance, in the Euclidean, in the upper half plane model of the hyperbolic plane, we see that our orientation preserving isometries are they are just conformal maps, and orientation reversing hyperbolic isometries, these are which are reflections, they are anti-conformal maps, right? That's the point. Okay. Then actually this is like a general, this is a more general proposition, which I'm going to write down here. That every inversion is a smooth and anti-conformal map. Okay. Let me, okay, in the models, right, in the conformal models, BD and UD, we have the following. The inversions actually I can define inversions with respect to lower dimensional spheres, right? The inversions with respect to with respect to Euclidean spheres, with respect to Euclidean spheres, which are orthogonal to the boundary, determined precisely in the respective way, right? Are they are anticonformal, right? Anticonformal, and thus orientation reversing isometries that map K spheres and K planes to K-dimensional spheres and K-dimensional planes that map K-dimensional spheres and K-planes to K-dimensional spheres and planes. But this set goes to this set. It doesn't mean that they go respectively. They can map a sphere to a plane and vice versa, right? K-dimensional spheres and planes. So in particular, this means that and moreover, the inversion and like the same holds for the inversion that maps the model BD to UD, right? Same is true for the inversion, which is I omega, that defines an isometry between BD to UD, right? So this is the picture probably is obvious, but let me show it. So we can have like spheres orthogonal to the boundary, or we can have planes, right, passing through the origin. And in the upper half space model, we also have planes and spheres orthogonal to the boundary. Yeah, this is my picture. And obviously, reflections in hyperplanes. Well, yeah, the first question is how to prove this. You just, so the proof, okay, a hint for proof. Write down the inversion in coordinates and just compute the differential, right? Okay, the hint is that I think that the hint is that we can assume that we like after translations and dilations, we probably can suppose that we consider I think that I think that we can consider the point. Let me think. Okay. Start. So the hints for the proof, right? Start in the model UD. It's enough to consider the sphere S centered at the point which is equal to, okay, with centered in the origin with radius 1, right? Origin with radius 1, right? Then inversion is, okay, then phi, right? Then the inversion looks simple. Okay, okay. This I with respect to this S is just the Euclidean vector X over the norm X squared, just like here, right? Precisely like here. So this is X over X squared. Find the differential, right? Compute the differential. Compute di of S. And you will see what happens. And then use the fact, okay, the hint number 2, combine inversions with inversions, basically, and you will see the results. So obviously, since our models are placed in the Euclidean space, right? We definitely consider just Euclidean spheres. So this is basically, it doesn't have to do anything with BD or UD, it's just the Euclidean fact. And but to see that this is an isometry, so the isometry part, you need to check that you preserve the Riemannian metric, right? To see that this is an isometry, you just need to check that. Okay. Let me write it down here. To show that these are hyperbolic isometries. Okay, isometries of HD. You need to show that the GU of any vector V, right, its scalar product with itself, is GU of, okay, the differential of I applied to V, and same here. Okay, unfortunately, I have not much space, but I will write di V, okay? So again, that's the idea. Then you take the Riemannian metric on the upper half space model, GU. Since you already compute, right? In part 1, you compute di, right? You compute di, you just have an explicit matrix representation of this. And then you plug into the metric, and you will see that the hyperbolic norm of the tangent vector V is equal to the the square of the hyperbolic norm is equal to the square of the hyperbolic norm of the image of the vector v with respect to the differential you just compute in part one. It's like some somewhat tricky technical computation, but not actually very lengthy. You will, yeah, it's possible to do. And yeah, that's the hint for proving this proposition. And let me check what is in my plan. Yeah, and yeah, but basically for the Bohm model, you just apply the inversion. Yes. But again, in the Bohm model, yes, you just yeah, I think that it's better to just start with UD and then move to the Bohm model. Yeah, I think that's the best way. Okay. Yeah. So the inversions are anticonformal. What is interesting that the composition of two inversions is already something conformal, right? So the composition of two anticonformal maps is conformal, and it basically depends on the parity of the number of inversions you use in your decomposition. Yeah, that's the nice fact about this. Okay, then I think that okay, so the totally geodesic, I wanted to think about totally geodesic. Yeah, so in fact, the spheres and okay, so from this fact, we see that these are isometries. And in fact, I think I want to show, yeah, but probably let's make a break, a 10 minutes break, and then we will discuss that, in fact, the isometry group of this model or this model coincides with the group of conformal maps of the boundary sphere. And in fact, our k-dimensional spheres and planes passing through the origin. Okay, or planes passing through the origin here, or k-dimensional spheres and planes are orthogonal to the boundary. These all are precisely all possibly, like give you all possible totally geodesic planes in those models respectively. Yeah, that's the main point. And yeah, then we will see probably some other isometries. Okay, let's make a break.
We know that stabilizer of G is like prime on A, and this
Since yeah, maybe let's actually record this. I will show it on the board. So you can just look at the matrix. So basically we have matrices where should I? Okay, yeah, I will write it here. So the point A is just 1, 0, 0, 0, right? And you want to take all matrices from OD1 prime such that AA is A, right? But then you see that your matrix is just some D plus 1 matrix, and you multiply it by the column 1, 0, 0, 0. And what does it give you, right? You just multiply this. So this implies that, well, it gives you just the first column of this matrix, right? But it should be 1, 0, 0, 0. So in particular, this implies that here you have 1, 0, 0, and so on, 0, right? And thus your matrix has, yeah, one top left entry and this is just D times D matrix. And since you have the condition that it preserves ID1, right? So this matrix, okay, let me denote it by B, right? You then look that 1, B should preserves -1, 1, and so on, 1. And the block B acts only on this, right? So the matrix B preserves the standard ID -1. Oh, actually, I probably, no, it should be just ID, right? And this matrix is ID. So this block, okay, I will remove units from here and I will just write here ID, right? So B precisely corresponds to this block in this quadratic form. So B is, by definition of the orthogonal group, is just an element of OD. Well, and vice versa, you can definitely take any matrix which is just 1 something and B. Well, you can just take, yeah, 1B, the block diagonal, and it will preserve the matrix, right?
Besides the description of what
Yes.
like OT1 have A transpose ID1, A plus ID1.
Well, for, yeah, but OD1 prime is just a subgroup of OD1, right? So we just simply take those that do not like switch.
Just not like the degree to index to
Yes, it will be just an index 2 subgroup, right? But yeah, the point is that generally you can like what is the problem with OD1? It can send the point A to -A, right? So so in fact, yeah, you're actually right. You're actually right. I don't need here O prime. Once you say that A is equal to A, then it's already, the stabilizer will be still orthogonal group. Right, yeah. So the stabilizer of, even the stabilizer of OD1, okay, of the point A in OD1 itself will be also equal to the orthogonal group of order D, yeah. Right. So once you want to fix the point, it's the same compact group fixing the, yeah. It's like just you can think of the hyperboloid as a manifold with 2 connected components, but the stabilizer of any point there is the same. Yeah. Okay, yeah, let's make a break. Okay, so let's continue. But before continuing, I need to give a comment. So the first is that OD prime 1 is indeed, well, is actually the maximal subgroup, right? The maximal subgroup of OD1 such that it preserves HD. So it eventually, well, it just consists of all elements of OD1 that preserve HD. This is how you can explicitly obtain this group, right? Okay. Then right, and then one more remark that, okay, yeah, there is another subgroup of OD1 also of index 2. For example, okay, there are other subgroups of index 2. For instance, you can take SOD1. so which consists of all matrices preserving ID1 such that the determinant is equal to 1. And SOD1 not always preserves HD, right? You can take such, so it depends on the parity of the number D, right? And for odd dimensions, the isometry, okay, the map V to minus V, it doesn't preserve HD still, but it belongs to SOD1, since if D plus 1 is even, then definitely the minus identity matrix has positive determinant, which is just plus 1. Okay, now I would like to move to, okay, I would like to continue discussing the isometries and totally geodesic planes. Okay, and we just proved, right, we just proved that the isometry group is generated by reflections, and we are going to discuss further these models. Okay, then I think that it's okay. So as a consequence, by the way, so the idea was to show that. Okay, I said that the proposition we're going to show. Right. So I proved that any. Okay, so I proved that inversions are isometries, right? And I wanted to. Yeah. So and we proved that any isometry is at most is the decomposition of at most is the composition of at most D plus 1 reflections. And I also wrote down something, but I forgot what I wanted to say. There was a proposition right down here. Okay, anyway, it's just so for me, what is important that okay, right. So what is important that in the models BD and UD, spheres and planes orthogonal to the boundary are okay. They kind of give all totally geodesic. Give all totally geodesic planes in the corresponding models, right? Oh yes, yeah, I remember what I wanted to. Yeah. So in fact, again, I will give something like I think I will give something like a hint to prove this theorem. Okay, to prove this proposition. Okay. First of all, so one of the possible approach, consider first the hyperplanes, right? The codimension one case. And then you need to show that indeed hyperplanes passing through the origin or the like spheres orthogonal to the boundary are okay. Then you probably can consider, yeah. So I first consider the map, right? The codimension one case, and then just simply look what is the image. Okay. Take. I forgot how I denoted Xi, right? Xi was my map. Okay. It is known, right? It is known that H, which is HE, is a totally geodesic hypersurface in the hyperboloid model, right? So we have this vector E, and we have HE. I think that you need then consider separately two cases. One case is when E belongs to the tangent space of this point A, right? So this is the point A. Okay, I will not pick it here. So analyze, right, separately two cases when this vector E belongs to the tangent space of the point A, where A is, okay, it is just 1, 0, 0, 0, right? So if it is so, what do we have? We have that the first component, right? We have that the first vector, okay, the first coordinate is, okay, in this case, it is kind of just horizontal, right? So two cases, 1 and 2. Here, E is horizontal. And the remaining case, E is not horizontal. That is, E has some coordinates, I don't know. What should I think you can write down that it has, okay, 0 is not nice, but let me just choose some, I don't know, numbers like S, then probably you have some number of zeros. I think up to, yeah, actually up to isometry, it does matter. You can think that S, 0, 0, and 1 in the end, right? So this is your vector from RD1, such that the first component is S, and it is not 0, since since E is not horizontal. So two cases. Then look at the image. Then consider Okay, so yeah, the image of under and consider psi of HE, where psi is this projection from HD to BD. Okay. This is like the hint how to show that. Okay. So then you first consider codimension one case, and then it remains to notice that the intersection of hyperplanes, so any plane in HD is an intersection of some number of hyperplanes, right? And right, and the point is that totally geodetic submanifolds move, well, they are mapped to totally geodetic submanifolds under isometries. So since we know the description of all totally geodetic submanifolds in HD, right, then we obtain this. Okay, right, and the last, and the next step is, and then notice that every plane is the intersection of hyperplanes. Okay, notice that every plane is an intersection of a finite number of hyperplanes. Okay, yeah, that's about totally geodetic planes and the corresponding models. So yeah, I already drew the pictures. Now I want to also I want to write down a few other important facts. Oh yes, now I remember why I needed this. So the proposition now it is basically the following theorem. Okay, I will just start with a picture and then we will try to write down what is the consequence, right? So let us take first, it actually doesn't matter, but let us take first the upper half plane model. So let it be the reflection, so H1, this is H1, the hyperplane, right? And this is H2, another hyperplane. So H1, H2 are hyperplanes. These totally geodetic subspaces in HD, currently considered as UD, right, in the upper half space model. RH1, so the question is how are, okay, RJ is RHJ, just for simplicity. We have two reflections. So it's, I will write this down as a just a fact. So, or lemma, I don't know. RJ then act on the boundary DUD as what they act as conformal maps, actually. The action is okay, it is probably anti-conformal, right? Yeah, so let's look. Yeah, it should be anti-conformal, correct? So indeed, look here. R1. Okay, it's kind of proof. R1 fixes infinity and acts as a Euclidean reflection in R d minus 1, which is just the boundary, right? Which is the set of all points in UD such that xd is equal to 0, right? Okay. It's a little bit messy, but this is how it is, right? So this is my boundary hyperplane. If it is defined by the coordinate xd is equal to 0, right? So R1 just acts as a reflection in this. Okay, R2, what's going on with R2? R2, it interchanges the center with infinity, right? And it acts also as just the Euclidean inversion with respect to, so let me denote this boundary. So, okay, R2 acts as a Euclidean inversion I with respect to small s, where S is the intersection of H2 with the same RD minus 1, right? So S is can be identified with just D minus 1 dimensional sphere. No. What is the dimension? So this is the dimension D minus 1, so it's the dimension D minus 2 dimensional sphere, right? D minus 2 dimensional sphere. So it is a Euclidean inversion with respect to this. Acts as a Euclidean inversion with respect to D minus 2 dimensional sphere, right? So the action on the boundary is just, okay, now I'm writing the corollary of this consideration. Any isometry okay, any isometry gives thus a natural conformal or anti-conformal map on the boundary, right? So any isometry gives a natural anti-conformal action on the ideal hyperbolic boundary, the ideal boundary G infinity HD, right? And that is, as a corollary, we have that any isometry extends to the self-homeomorphism of the ball, right? So the first corollary is this one, and the second is about this extension, right? The proposition from the first part of this lecture that any f from HD to HD extends to the self-formula f bar to HD bar. And this fact is very important. right? Okay, so and yeah, and along the way, I think we I think that I should write down that basically we just proved the following theorem, right? We just proved so I'm writing we just proved the following theorem that the isometry group, the orientation preserving isometry group of HD is isomorphic to the group of conformal maps of the boundary of HD, which is precisely the conformal group of the d-1 dimensional sphere, right? This is what we just proved. And the full isometry group is okay, sometimes actually okay, this is a bit confusing. Sometimes people denote by conf of SD-1 the group generated by inversions with respect to the spheres. Okay, maybe it's not, I'm not sure, maybe it's not very good. But in the full isometry group of HD, I will just write this down. And this is isomorphic to, I don't know, conf tilde of SD-1 generated by all inversions with respect to codimension 1 spheres, codimension 1 spheres in SD-1. Okay, so this is basically our theorem. And as a corollary, we have that, well, isom plus H2. We already know that it is equal to the group of PSL to R, right? So I can kind of say that we proved it independently, right? We proved it independently a few lectures ago. But what we didn't prove is that the orientation preserving isometry group of H3 can be considered, well, can be viewed as the group PSL to C. And this just follows from complex analysis. So again, part 1 and part 2 follows from complex analysis. Follows from complex analysis. It is the theorem that the automorphism group of the extended C, right? Since the boundary, right? The ideal boundary of U3, it is just C bar C extended with infinity, right? I can view the upper half space model for my so I can view U3 as ZT, where Z is complex, G is positive, right? And then I have a natural action of the isometry group of H3 on the boundary, as we just discussed. And then its orientation preserving subgroup acts as just conformal group, of the group of conformal automorphisms of the C bar. And this is known to be the group of all complex fractional linear transforms mapping C bar to itself. And its group is well defined. It is PSL2C, right? The group where all A, B, C, D are, are included. Okay, yeah, that's actually, this is very important. And yeah, so we just take the matrices A, B, C, D with complex entries and the quotient of PSL2C, right? It is just a set of A, B, C, D, where A, B, C, D are complex, AD minus BC is equal to 1, and we want to take the quotient by plus minus identity. And the action of, right, so in the action, and the action of PSL2C on the boundary is precisely by, so this is isomorphic to PSL2C, and these guys act as just fractional linear transformations, right? So this is very important description of my isometry groups. Okay, now we are finally ready to prove the general theorem of the classification of hyperbolic isometries. And I think that this will be the end of our lecture before this break for the reading week. Okay, so let me first, yeah, okay, so I'm just going to write down this. Actually, I have two important theorems, but okay, yeah, I want to in fact, I want to take I want to give a description of not only isometers but of relative behavior. So theorem, okay, relative behavior of a pair of planes in HD. Okay, so let S and S prime be two planes in HD. Then only the following options are possible. Then only the following or configurations are possible. So the configuration number one, the intersection is not empty. So S intersected with S prime is not empty in HD. Number two, they meet only they meet at the boundary point. So we say that S with S prime is empty, but the compactification of S, right, with the compactification of S prime is some boundary point on HD. And the third, even that even the compactifications do not intersect, right? The third case is that even the compactifications do not intersect, is empty. So intersection of the planes itself is empty, but they meet on the boundary. And yeah, in this case, so the pictures, I will have three pictures in the ball model. Okay, so for instance, here it is my plane S, and suppose S prime is a plane, so it is a surface. Okay, right? It's a sphere, and this one is a line. Okay, so it is S prime. S prime is a geodesic. This is a geodesic plane. They intersect. Another picture is that they can touch each other. So I have a plane S prime, which is currently also a geodesic, and I have a, again, I have a sphere, such that sphere and plane, they touch, they are tangent to each other at the boundary point from the S2, which is the ideal boundary of H3, right? It's like a three-dimensional picture. And another case is this. I have a geodesic S prime, and I have a geodesic plane S, and they do not intersect even on the boundary, even their compactifications do not intersect. And then we have a common perpendicular. So in this case, there exists a geodesic gamma, which is orthogonal to S, and which is orthogonal to S prime. And this, it obviously realizes, okay, actually I need another color. I'm not sure it's really visible on the video, but I hope. So I'm taking the blue. Right, in this case, I have a orthogeodesic, which intersects both planes orthogonally and thus realizes the distance between these two planes. Well, basically, this just follows from the description of totally geodesic planes we obtained, but I think that you can just show that if, okay, then I think that the hint to prove this theorem is the following. You consider two compactifications of your planes, and you imagine that they intersect. Well, first of all, it is obvious, it is like easy to check that all these situations are possible. I just basically drew them right here, right? But then you take two compactifications, consider their intersections, and assume that you have 2 points, P and Q, right? Suppose that they contain at least 2 points, right? But if they contain 2 points, then you have a unique geodesic connecting these 2 points. And in this case, this means that the intersections of the planes itself is not empty, and you basically move. You obtain the case number 1. Well, it's just a hint, but you can do it. Okay, now I want to prove. Like right now, I will just write down this theorem here, but the proof simply follows from our discussion during today's lecture. Yeah, do you have a question?
Like, I thought S should be like
Which one?
second.
Here?
Yeah, it's
Well, yeah, it's just like a not careful picture, but these are perpendicular to the boundary. Yeah.
okay. Yeah.
So the most you can start with drawing a diameter, and then you can actually draw infinitely many like sphere heads orthogonal to the boundary. You just by changing the center, you vary the center. So you assume that your sphere, you want the sphere to pass through this point, then you take a sphere orthogonal to the boundary such that it dashes to this point. Actually, if you choose the center, this sphere is uniquely determined by this condition. If you choose the radius, definitely you can take, well, if you vary the Euclidean radius of the sphere, you will get, of course, infinitely many spheres with given radius passing through P, since you can basically take the whole sphere around. Yeah, okay. Oh, yeah. So that's the idea. And yeah, and now we prove the following theorem. It's the classification of hyperbolic isometries. Classification of isometries of HD. So let F be an isometry, right? Then only the following options are possible. Then one of the following holds. Like, and precisely one, then precisely one of the following holds. So the first is that the fixed point set of F in HD is not empty. And these are called elliptic isometries. Elliptic isometries. The fixed point set of F with HD. So the second case is that this is empty, but the fixed point set of the extended F, right, with the boundary is just one single point. And the third possible, The third possible case is that this fixed point set of F itself is still empty in the interior, right? But we have 2 points, 2 fixed points of the extended F on the boundary. These are called parabolic isometries, and these are called hyperbolic isometries. And the proof is actually very short. I will give it here. So I'm drawing the picture, and I assume I have 3 fixed points. But first I need to write that by the Brouwer fixed point theorem, by the Brouwer fixed point theorem, F bar has fixed points in the closed ball, right? F bar has fixed points in the closed ball. HD bar, right? Assume that we have 3 distinct points on the boundary. That we have 3 such points on the boundary. Then look at this picture, and one can say actually the following. One can prove that the geodesic is invariant, right? The geodesic is invariant with respect to F. Okay, I think let me now go to the right word. Okay, so the proof, continuation of the proof. Then geodesic PQ is invariant under, okay, it is invariant under F bar, right? But actually it's invariant under F since it's restriction. And it means that it doesn't fix it pointwisely, but definitely the points from geodesic belong to this geodesic. So it can like move them somewhere, but we don't know how. Then take another geodesic that is orthogonal to this one. Well, it's actually, okay, I will leave it as an exercise. Right, that it is invariant. It requires some considerations, but it's like geometrically the intuition is like clear, but yeah, the details are obviously important. Then another geodesic L1 So, okay, that would be L1, this PQ, then geodesic L2, which is orthogonal to L1 and R belongs to L2, so also geodesic. Is also invariant, is also invariant under F. Then the point X, which is the intersection, then X from L1 and L2 is also invariant, and thus f of x is just simply x, and it is a fixed point from the interior. So that is, we have that the fixed point set of f, right, intersected with HD is not empty. And so we obtain elliptic. So therefore, f is elliptic. And then you just need to consider, well, then I am saying that the proof is over, since it remains to consider two distinct cases. When you have 1 and 2 fixed points on the boundary, right? So I'm writing, right? This is because it remains to consider f with the with the cardinality of the fixed points on the boundary. Yeah, let's recall then 2, right? And then you will get parabolic and hyperbolic isometries. So we already discussed different types of hyperbolic, parabolic, and elliptic isometries in low dimensions. Then probably I think I'm going to just publish a set of exercises where you will play more with this, with hyperbolic and with these different types of isometries in higher dimensions. And some of these might appear in your assignments. That's the idea. Right. So, but the classical types are still the same. Elliptic, for instance, are reflections or reflections with respect to low-dimensional planes. Rotations around geodesics, rotations around points in the plane. These are elliptic guys. Parabolic, typical parabolic ones are in the upper half plane models. They can be viewed as Euclidean translations along the horizontal hyperplanes. This is an upper half space model. And but not only, right? We can have more complicated ones. And hyperbolic just are translations along geodesics. And well, those can be present. We will discuss isometries probably in a bit more details already after the reading week. But like very soon after that, we start already discrete groups. So now it's really a logical break. And like the next lecture, I hope to start the discussion of discrete groups of isometries. Probably I will give some maybe since it's just 1 hour lecture, it will be a short introduction with some elementary transformations, but it will be already a preliminary lecture for discrete groups. And then the thirds after that will be about discrete groups in general, their definitions, and probably fundamental domains and so on. Okay. Yeah, I think that's all for today. Thank you.